Okay. So, yeah, so let's get back to where we were. So, what we've been doing is Markov decision processes essentially. We started off with that. And so we saw like different things like, you had states, you had actions, you had transitions, and each of the transitions had some probability, right? And there were these rewards associated with each transition. And at each time step you got a reward, and your idea was to maximize the long term reward. Okay, you wanted to basically find a policy which maximizes your long term gain. Okay, and what we saw earlier in the last week was, if you know the structure of the MDP well, you know how to go about. Okay, so yesterday we did this kind of roadmap of whatever we did in the previous week, right? Like, you started off with some policy. There were a couple of problems. So one was evaluating a fixed policy. So where a policy was a mapping from a state to action, and so one was evaluating a fixed policy. We saw some techniques. And then we went to a slightly harder problem of finding the best policy. Okay, what is the best? Which one gives the best value? And there we saw a couple of algorithms. Okay. So now we added. So this was a case where you knew everything about. You didn't know exactly which state you're going to land up once you take an action, but you knew this transition probability. So this TSA S dash was a probability of reaching S dash, starting from S and taking an action A, and this parameter was known to you, and so was the rewards. Okay, so yesterday what we said is, now we are going one step further, where we don't know these probabilities. We don't know these transition probabilities. So these numbers we don't know. We also don't know these rewards. And we saw this example, kind of simplified example, where there were these two restaurants and you had to choose between them, but without knowing what's the probability of each of these rewards. The new restaurant had 0 or 200. You didn't know the probabilities. So this was a setting where you knew the rewards for the new restaurant, but you didn't know the probabilities. But generally, even maybe the rewards also are not known. You will know only once you try it. Okay, so this was the framework. And so this could be captured using an MDP itself. But this time, these numbers are not known. These transition probabilities are not known, and more generally, even the rewards are not known. Okay, so so this set of problems, we called it as Bandit. So where the states were really not giving much of an value. So actually, the example I told you was a very simplified example where, you had these two restaurants and all that. But you see, these kind of problems are, really useful even in industries. Okay, for example, in Google, okay, so they have these sponsored auctions, I mean, sponsored ads, right? If you search for some keyword, it shows you a list of ads on the top. Okay, the sponsored ads. And what happens is, each time somebody clicks on these ads, Google is making some profit. Okay, and the profit is being given to them by these third parties for whom you are making these ads. Okay, so maybe it's a shoe product and this is an ad of a shoe. Okay, so the company who is making these shoes is going to give some monetary benefit to Google each time their ad gets clicked. Okay, so now here is there's a choice to be made here, right? Which ads should Google put on their page? And what is uncertain is, you don't know if these are going to get clicks or not. So beforehand, Google doesn't know anything about, whether these ads will be clicked. And if an ad is clicked, there's a reward. If the ad is not clicked, that's no reward. Okay, so it's exactly the same kind of problem that appears here. So this is just to put this in perspective on, where such problems arise. It's, of course, we saw this thing of restaurants making a choice, but these kind arise even in larger industries also. Okay, so to capture generally these MDPs where you have these transition probabilities and reward probabilities which are unknown, what you need is some kind of data, right? Some experiences basically. And from your experiences, you can try to learn these these unknown quantities, these two basically, the transition function and reward function. So that's what we saw yesterday. So we saw this example of a grid world, right, where there's some episodes which are given to you. So episodes is like you start off from some state and keep going till you reach the exit. So what policy was followed here was not very critical at this point. So you can just think of it as there's somehow you got this data, and then you try to estimate the transition probabilities and the rewards. You try to get a sense of it from the data. Okay, and once you had this, if you had enough samples, you could get these numbers and then use value iteration or policy iteration to get the best policy. Or if you wanted to evaluate some fixed policy, now you have these numbers, use that instead. Okay, so this was what we called as model based learning. Okay, and so this is a very first way to think of it. uh, Try to explicitly learn the parameters of the MDP, and then apply whatever in MDPs. Okay, but the issue is this kind of a split, right? How much do you need to learn, and at what point can you start? What point is enough? Okay, how do you know that you have learned enough or not? So these are some of the questions, and of course you only learn about what you have seen in these episodes. So you need a lot of samples. Okay, you need a lot of episodes to learn something meaningful. So in that sense, this model based learning idea, yeah, it's a first approach, but it's not really something that you want to persist with. So going further, you want to do something better. Okay, so here I just want to also talk of a slightly simplified version, as it's a slight detour. So consider this problem that I want to find out what is the height, what on an average, what's the height of third year engineering students in India. So it's a slight detour. Okay, so I just want to illustrate an idea, so that's why I'm doing this. So I want to find out what's the height of third year engineering students in India. Okay. Uh, yeah, so this is actually, you can think of this as a random variable edge. Okay, it's random in the sense that there are a lot of other factors that, I mean, your sample space has a lot of other things, right? Like what was your nutrition level? Maybe it has something about some hereditary information, how tall were your parents and all that. So all these factors contribute to what your height would have been. So it's a random variable. Okay, and now I want to somehow estimate it. Okay, I want to estimate the average height. So I want the expected value of the height. So this is the expected value. Okay. Uh, so from your probability class, you know what the expected value of this random variable is, right? So you remember this definition, I guess. So this is just the probability of all possible values the height can take times the h, right? So this is something that you would have seen in your probability class. Now I actually want the expected value, but I don't. I mean, maybe I don't know these probabilities. Okay, so what do I do, right? So if I have this kind of it's a simple estimation problem, right? What I would do is, I know you're all doing my AI class. So I ask each of you your heights, okay? And maybe you tell me some numbers. So maybe I got some data. So uh, okay, so maybe I'll just write some names. I'll just tell some heights. Okay, it may be wrong. Okay, but let me just write it here. So Akshay maybe 160 centimeters. I don't know if it's tall or low or whatever. I don't know what Akshay looks like, but I'm just writing this. Okay, so maybe this was an estimate I got. Then maybe Tanuja, I got some other estimate. So maybe 158. So pardon me if these numbers are way off. Most likely it's going to be way off because I don't know you, not seen you. So like this, I'll get some numbers. Okay. And what I can do is maybe one way I can do is, maybe somebody else, maybe Rishabh. Okay, Rishabh is also having a height of 160. So what I can do is I can try to estimate the probability of these numbers. Okay, so maybe with 160 there were like maybe 5 students, and the total number of students was maybe 50. Okay, so I got something like this, 5 by 50. And with 158 maybe there were like 2 students, so I got some estimate like this. And so whatever data I have from the whole class, I try to get these estimates for the probability. So I put this hat because it's an estimate. And then what I do is I can compute this expectation using these estimates. So what I will do is now an estimate for the expected value is just the all the probability estimates I have times h. Okay, so this is one way I can do, right? Now another way, and so this is estimate one. Okay. Now, another possible estimate is I can just take whatever numbers you gave me. So let me call this sample one. So H1, H2, like maybe let me not call it H1, let me call it S1. So this is sample one, this is sample two, and this is sample three, like that. Okay. So all these are samples of the random variable H. Okay, so what I can do, instead of doing this estimate one of finding the probabilities and computing this, I can just take the sums of all these samples, right? So S1 plus so on plus some S50, 50 students. If there are 50 students, I got this number divided by 50. Okay, so this is another estimate. Okay, Um so why can I do this sum of all these by 50? There is some theoretical reasoning on why this is a valid estimate. Do you remember this from your probability class? Something you learned in probability about why this is a reasonable estimate. If you have large number of samples, this will be close to the true expected value of h if you had a large number of samples. Do you remember what this was?
Law of large numbers, I think.
Yes, exactly. Because of law of large numbers, this was a reasonable thing to do. Okay. And so here you see there are these two ways of estimating the expected value. And actually, both these are going to give you the same number. I mean, the way you estimated the probabilities was just the number of students with this height divided by the total number. And if you look at this expansion, that probability is also going to come in, right? It's just that you're taking each of these, you're splitting these 5 by 50, like you're taking it as 1 by 50 times one, this number 160 plus 1 by 50 times 160, like that you're splitting it. That's the only difference. But you see, there are these two approaches, and actually, whatever we are going to do next is just a distinction between these two. So, this approach, this estimate one, was kind of what you saw in model based learning. Okay, where you explicitly find out these probabilities, these numbers, these parameters to do any further computation. Now, in this estimate two, on the other hand, is like you're just directly doing some operations with the samples to get the expected value. So this is, you're not actually learning these probabilities beforehand. Okay, so this is called model free learning, and this is actually a slightly more useful concept, because it avoids the hassle of doing several things. Like you're getting the finally the same estimate, but with some simpler operations. Okay, so what we're going to do now is on model free learning in MDPs. Okay, so model free learning. Uh, so in RL. Okay, so RL is just you have an MDP and you're learning the transition probabilities and the reward functions, and we are going to go for a model free learning approach. Okay, so again, I'm just going back to this example that we did yesterday. So let me just copy this back. Okay. So what I'm going to do now is so model free learning is what I will do. So remember, like your ultimate goal is to get the best policy in MDPs. So model free learning in MDPs. Uh, but what I want to do is, okay, it's a lot of information to do. Like I have some training data, and now I also have to somehow learn the values, have to learn the best policy. Let's not go into too many details at the moment. Let's start with a slightly simpler problem. Suppose I have a fixed policy pi. So I have a fixed policy pi, okay, that's given to me, and I have some samples of this policy. By that, what I mean is I have some episodes where somebody tried out this policy and told me the rewards they got in each step. Okay. Now, with this information, can I estimate? Can I estimate V pi of each of the states? So remember, V pi is the uh, value of state S under policy pi. Okay, I want to somehow learn this number, but the issue is I don't have the transition probabilities. So if I knew the transition probabilities, what I would do is, so V pi of S, I would just use this equation, right? So the transition probabilities you take, and then times whatever reward you're going to get. Okay, so this is what I would do, but I don't have this number. Okay, so now how should I estimate this? Like remember the even before we talked of these computations, we discussed how what this value function is. You had this notion of discounting. So essentially it was the first reward you got plus gamma times rt um, at the next stage, right? So rt, okay, so what you had was r1 plus gamma times r2 plus gamma square times r3, like that, right? So this was the reward function actually, and the value was exactly this, right? So maybe I shouldn't mix up these two notions. So let me just I'll just remove this for now. So so let's just take this episode 1 for instance, right? So the total reward that you get if you start from B is, at the first time step, you were going to get -1. And the next time step, you were going to get -1. And the last time step, that was the terminal state, you were going to get 10. Okay. So in episode 1, what this means is that, our rewards from B, or the utility, or, the value from B. So this was just, if you look at just this one sample, it was -1 plus gamma times -1 plus gamma square times 10, right? So this is, you remember this, right? You had this notion of discounting. And similarly, the value from C was, if you started from here in this episode 1, you were going to get -1 plus gamma times 10, right? Is this clear? Like whatever I've explained, I've just told you like what we meant by, when we said the value of a state, this was what we wanted. Okay. And what I'm showing you is for this particular run where, you start from B, go east, you reach C, then you again go east, you reach D, and then you exit. For that particular sequence of moves, what was the value of each state? Okay. Um, so, yeah, so I have some information here. So, now can you tell me what would be an estimate for the value of B? So, what this data is actually is a policy pi. So, in this case, the policy pi is what is given here. So, from B, I'm going to go east. From C, I'm going to go east. Okay, and from E I'm going to go north. This is the policy here, and what I have with me is some runs of this policy. Okay, and whatever rewards I got. So episode 4, what happened is I started from E, then I took the north as the policy told me. I went to C. So I took north, I actually went to C. But at C, I took an east, but however, I landed up in A because of the randomness in the system, the probability of which I didn't know. Okay, so this data is given to me. So, I can get an estimate for the value of B from all these four episodes, right? So if you can, so value of a state is a random quantity here, okay, because you don't know, there is some probabilistic information because you don't know which state you're going to land up in, and there is a value associated with those states also. Okay, so using this idea, we saw this model free learning idea, right? You have these samples and you divide by the total number. Okay, so can you think of what it evaluates to here? So if I take value of B, right? So how would I find under this policy pi? So these are all runs of a policy. So can you tell me what would, okay, let's take the first sample. What would be your first sample value? Can you give me one estimate of the value? Let's take gamma equals 1, just for simplicity.
9, sorry, 8.
8.
8. So what you have told is this value, right?
Yes.
Yes. So from the first sample, so let me just write it here. So sample 1 is 8. Okay, sample 1 is 8. Can you give me one more sample of it?
For sample 2, it's also 8.
It's also 8, right? Yeah, same computation. And so here I have two samples. So what I can say is, so B pi of B, my estimate is 8. So it's 8 plus 8 by 2. So it's 8. Okay. So this is one way. Let's just do one more computation. What about value of C? Can you give me one sample? So there are four samples I can get here. So let me take one sample first.
9, 9, 9,
9.
minus 11.
Yeah. So 9. So this one, right? The first episode has a minus 1 and 10. So you have a 9. And sample 2 is also the same thing. So you have a 9. And in sample 3 is also the same, 9. So from episode 3, I will get an estimate of 9. And from episode 4, it is minus 11.
Minus 11.
Okay, so right, so minus 11. So basically I can add up all these. So B pi of C, my estimate is going to be, so 9 plus 9 plus 9 minus 11 by 4. So 4 samples I have. Okay, so what's this number? So
4.
4.
yeah, but okay, so it's 16 by 4, 4. Okay. Okay, so like this, you can proceed and you can find the values of all these states, okay, under this policy. Okay, so this is kind of doing a little better than, estimating this probabilities and then doing a value iteration. Okay, so in that sense, it's reasonable. But again, the thing is, you need a lot of samples, and there's also this factor about, you treat each of these samples, independently on their own. Okay, so okay, this is a reasonable method. You could do this. Now the question is, can we do something else? Can we do a better approach? Okay, so this is method one, and this is called direct evaluation because you're directly taking all the samples, whatever you need, you're computing exactly from the episodes and doing your computation. Okay, so the names are not so critical, it's just the ideas that are more important. Okay, so I'm just going to try to develop another method. Okay, so here I'm going to try to use something we did in policy evaluation, like what you did in MDPs. I'm just trying to I'm going to try and use those updates and see if I can somehow get this notion of samples there. Okay, so here if you see, I didn't use any of the Bellman equations, I didn't use any of these those recursions here. So I explicitly computed these values, but instead now what I'm going to do is, I don't want to compute all these numbers like this. I don't want to expand what happens from the start to the end all the time. I want to do something a little easier. I'm a bit lazy, so I don't want to do all this. Okay, so what I'm going to try now is build on policy evaluation. Okay, so build on policy evaluation. There was this iterative method, right? So let's just do a recap of it. So iterative method for policy evaluation. So remember, like uh, you were you wanted to evaluate this fixed policy, and one thing that we saw, like if you knew the transition probabilities and the rewards, what you do is you fix this value v0, right? V0 of pi of a state s. So this was like the value of s under pi if there were zero time steps left, under pi if there were zero time steps, if zero time steps were left. And so similarly you had generally vk pi of s. So if you had k time steps left, this was the estimate. Okay, so I'm going to try and build on these ideas. So what I said there was, at the k time step, right, what happens is I'm at s, I take some action, I go to S dash. So I'm sorry, this is going to keep coming up again and again, this kind of a graphical, because it's easier to write these equations if you know, I mean, if you think in terms of this graphic. Okay. So yeah, so you took an action and there was some randomness here and you landed up in S dash. Okay, so the expression we had here was, okay, and the value here at S dash was Vk minus 1, right? Or let me just say Vk plus 1 here so that this becomes Vk. Okay, so Vk of S dash was the value at S dash. So what we said is we'll compute Vk plus 1 by seeing like what are the possible actions you can go to. So this was a transition probability. If you took an action A and you went to S dash, sorry, it's not A, right? Like the action is fixed here. Okay, so this action here is now because we're evaluating pi. So this is pi of s. Okay, so now the summation is over all possible s dashes where you can go to. Okay, so starting from s, you take the action pi s, and where could you reach? Times the reward that you would get from taking this action pi s and going to s dash, plus gamma times vk of s dash, because that's the reward at this point. Okay, so this was the setup we did, and we did this many times to get vk plus 1. Okay, so that was the case where you knew the transition probabilities. This was known and this was also known. Now you don't know this, but all you're seeing is some samples. Okay, so you are going to see some samples of this reward. Okay, and with that, can you just compute vk plus 1? Okay, so one thing, I think I already mentioned this yesterday, but just so that it's clear, this is actually an expectation. Okay, so this is actually the probability of being in S dash, given you started off at S and took an action pi S. Okay, and so this is a probability, and this is some actual value that you're going to get. Okay, so this is in some sense this whole quantity here with the summation. This is an expectation over all possible S dashes, all possible destination states, and the quantity, the random variable is, of course, this is the reward here. We're not considering it as a random variable, but it's a constant which you don't know. But let's just put it inside the expectation, because it depends on this S dash. So in that sense, it's a random quantity. So the reward of going, the one-time reward of going from S to S dash, plus gamma times Vk of S dash. Okay. So this exactly Vk plus 1 of pi, what you actually were trying to compute is an expectation. Okay. And now what we have is we don't have these probabilities, but we have some samples of the reward. So we have some samples here. So can we use the sampling idea to, can we do some kind of an average to get this expectation? Okay, so an average over samples. So here what the sample could be was you started off with V0. Now you are at some intermediate stage. The sample 1 can be whatever you did with S, right? Like you started off with S and took an action. So one sample is um, rs pi s, and wherever you actually went to s dash plus gamma of vk, gamma times vk of s dash. So you're going to start with v0 pi, and so when you start off, the first sample is rs pi s s dash v plus gamma times v0 s dash. Okay, and your second sample will be, maybe you started off with s, took pi s, but you reached s double prime, some other state. So then you can use vk of s double prime. So all this is under pi. Okay, and you can keep using many samples like this. Okay, and now for vk plus 1 pi, since you have this expectation, what you can do is you use these samples. Okay, so this is now just sample 1 plus sample 2, like that, and so on up to sample n. So if you had some n samples, this number, so no summation, right? So sample 1 plus sample 2 plus so on divided by n. So all these samples are basically what you have when you started off at S. Okay, so let's just, I don't know if there are any questions here. Maybe I'll just pause here for a minute. Was this clear, or is there some confusion on this?
The n will be equal to k plus 1, right?
No, so this n is actually the number of samples. So k is the number of iterations you do.
Okay, so the
Okay,
state S might not come in each sample. So
the
that's why.
state s might not. Okay, so actually what you want to do is you want the state s to come in each sample. So let's see it this way. So suppose you had all these episodes that were given to you at one go. You had these episodes, and then you're going to start this process. Okay, so then what you're going to do is you're going to start with v0. You're going to fix some capital K. So you're going to do these iterations till some depth K. Okay, so for K time steps, capital K time steps, and in each time step you're going to work with each of these samples. Okay, so there is a capital K that is for the number of iterations, total number of iterations, and there is also this n is the number of samples. So n is the number of samples you had for starting at S. Okay, so with this example, so if you were to start at C, so you're going to try to do these iterations for, let's just look at what happens if you want to see the value of C. Okay, so at C, how many samples do you have here, right, of starting from C? How many samples are there? Okay, you're all quiet. I need some response.
4, right?
4, right? Exactly. We just did this in the previous method, right? There were 4 samples of starting from C. Okay, but what you could do is your value iteration might, this, sorry, not value iteration, this process of repeating this v0 pi computation, that could have, like, you might go up to 50 iterations, right? Because you're going to start with v0, then you will compute v1 like that, and maybe you will go up to v50. Okay, something like that. But so that can be 50, but your samples will still be just 4. Okay, so there's a distinction between these two. Okay, so maybe I will just again take this example and maybe work out the value of C, just so that it's clear. Yeah, so So what's going to happen is now you have all this data. So I'm just going to show you some iterations of this method. So V0, so V0 pi of B, C and D, all these, I'll fix this as 0, right? There were 0 time steps left and this is what the values were. Now what am I going to do? I'm going to try and find V1 pi of B, okay? So in V1 pi of B, what I do is my sample 1 is this first one, right? So I took a move to C. I took a action to the east, and yeah. So the policy was fixed, right? So the policy here you're trying to evaluate. So for B it's east, and C is east, and E is north. I'm just writing it again so that it's more clear. Okay. So the first sample is I got a reward of -1 and gamma times v0, okay, v0 pi of c, right? So I went to c. So I'm going to use what I already know about c, okay? So v0 of c was 0. So I'm going to take my sample as -1, okay? Now the second sample I'm going to get from this episode. So here also it's the same, -1 plus gamma times v0 pi of c. So this will be -1. Okay, and so what I'm going to do in V1 is going to be, so V1 of V1 pi of B is going to give you -1. Okay, so this is not correct. You have to do this again many times. So let's just do one more state, right? V1 pi of C, let's try to just do it once. So can you tell me what is the first sample here?
minus
So
1 plus gamma times V0 pi of C.
so V0 pi of D, right? From
Yeah,
this,
D.
right? So -1 plus gamma V0 pi of D. So let me take gamma as 1 just for simplicity, okay? So here V0 pi of D was 0. So I'm just going to again get -1. And similarly S2, I'm going to get what? Same thing, right? It's the same set of moves here. So again, this is -1. S3 also is -1. What is S4? From this episode, if I started off with C, what should I consider as the value?
-1.
Minus 1.
Yeah, same, right? Because basically V0 is 0, but what you would do is V0 pi of A here, right? Because in this transition, sorry, yeah, you went from C, you took an east, but you landed up in A. So here you're going to look at A instead. In all these places, you would have looked at D because that's where you went to. So here everything was -1, and so V1 pi of C was going to be -1. Okay, so same thing you will do now for V1 pi of D. Next, so I will leave it as an exercise for you to do this. Okay, and so you will find V1. Now again, what you're going to do is you're going to compute V2 pi of B, V2 pi of C, V2 pi of D. Okay, so all this you will find based on what you've had in V1. Okay, and you'll keep doing this. Of course, you need to do it for A also. A and D are also terminal states, so you need to do this. So these here there is no actions, so no action takes place, but still you need to estimate the values of A and D also. Okay, so you will keep doing this and till at some point you will stop at maybe after
And can you
some
once write
iterations.
V2 pi of B?
V2 pi, okay, let's just do that. So V2 pi of B. So for that, let's take the first sample. So sample 1 is what we are going to see from episode 1, right? So what was the value? First, you got -1, okay? Plus gamma times, where did we land up here? We landed up in C. So what you need to be taking is V1 pi of C, okay? So V1 pi of C now is, you found it as -1. So this is going to give you -2. Okay. Now, again, sample 2, what will it
Okay,
give
okay.
you?
It's clear, ma'am.
It's clear, right? So the same thing you do. Now you will see some change in V3. Now after you do V2, now when you go to V3 of P, because you have 3 time steps left, that is where this value of D will come in, right? So in V1 pi of D, okay, so V1 pi of D was, you got a reward of 10. So here you're going to see a value of 10 if you complete these steps. And so in V3, this is going to also show an effect, okay? So V2 also you'll get it as a 10, and so that way it cycles, and finally it will converge to the right value, okay, if you have enough samples. Okay, is this process clear? Um, are there any questions? Can you just type in the chat box if it's clear or it's not, or whether you want me to explain something, some other parts.
So in this
Yes,
process, we like initially we run multiple episodes to get samples, and then keep
yes,
updating value based on the samples till convergence. That's
yes.
right.
Yes, you get all the samples first, and then you do these updates. Okay. Yeah. So the actually what you want to do is as and when you get your sample, if you can do some updates like this, that would be more ideal. Okay. So that's actually what you want to get to finally. But the issue is that in this step, right? So see how you are computing the values iteratively. So you need many samples where you started off at S. Okay. But now in these episodes, what happens? You will start off at B, you will go to C. Okay. Now, if as and when you get the sample, if you want to update the value of B, you need more samples of where you start off at B. So that means you take an action, you go to C. Then, if you want another sample, you have to come back to B. Okay, so that is the issue with this. I mean, you are not able to again come back and get another sample, right? But then you have to finish this episode again, do another episode to get the next sample. So that's why you cannot do this these iterations as and when you get the samples. Okay, that's the problem with this approach of trying to do the updates along with as and when you get the samples, right? Is it clear, Advait?
Yes, ma'am.
Yeah. Okay, so what about the others? So only Yash has said it's clear. I want to hear from more
Ma'am,
people.
I had
Yes,
this
Deep.
doubt. So, with every new sample we get, we'll also update the values.
With every new sample you get,
Suppose we'll get new values and we'll keep updating them, right? So, is it sure that it will converge ultimately?
yeah. So okay, so one thing I just want to clarify: so we are going to do this process once you have all the samples ready. So you're not going to do these updates as and when you get samples. So that's just one thing. I mean, I don't know if that point was clear. But anyway, so whatever you're going to do is after you have many samples. Yeah, so there are some guarantees for this in some sense. I mean, if you have enough number of samples, then you will possibly get close and closer to the value, because what you're effectively doing is an average, right, over many samples. And because you're doing this kind of a discounting, if you have these gammas as less than 1, whatever you had initially, that was a wrong estimate. So V0 was all wrong. But that gets, that fades and fades as you grow, as you keep increasing the number of iterations. So you need to have more iterations, and you also need to have more samples. So if you have this, then you'll possibly be close to the actual value. Okay, but it's not clear like if this is a proven fact, but all this is by seeing what happens empirically. Okay, is it clear, Deep?
Yes, ma'am. So, but suppose we have got a considerable number of samples and we have run the algorithm. But now, is it can we update it if we get a new set of samples? So suppose we experiment a little more.
You get some more samples, then whether you can update the values, right? That's what you're
Yeah,
asking.
yeah,
Yeah, that is a problem with this approach. I mean, because if you get samples on the fly, you're not able to do an update here, right? Because you where do you start off, like, at which b do you start, and where do you incorporate this new sample, right? That is an issue here. And in fact, to mitigate these issues, we have one more method, which is the state of the art, that's called temporal difference learning. So we'll go to that for so what you're asking is, as and when you get samples, can you just update it? And now later you get some more new samples after some period of time, then can you reuse what you learned so far and incorporate some new information, right, Deep?
yes,
That's your question,
yes.
right? Yes. So this is kind of an intermediate method. This doesn't allow for that. There are some issues here. So we will see how to deal with that next, actually. Yeah. So, okay. So all of you have found this clear. Okay. Okay. So I will maybe just stop the class here. So our next class is, we are going to do this temporal difference learning idea. So exactly based on Deep's question, Deep's and Advait's question, the flaws of this approach have come out, that you can't do an update in each sample. So next class we'll see how to go about that. Okay. All right. So let's stop here. I'll just hang back if there are more questions. If not, thanks everyone.